Hello there, and a warm welcome to the Sleepy Science Channel. I'm genuinely thrilled you're here with me tonight. Perhaps the day has worn you down, or maybe you're simply one of those souls who find solace in drifting off to sleep while contemplating the wonders of stars and gravity, rather than counting the proverbial sheep. In either case, tonight's mental voyage is crafted especially for you. There's absolutely nothing required of you but to relax. Allow your thoughts to soften like melting butter, let your breathing deepen and slow to a gentle rhythm, and picture your mind unwinding, uncoiling like a silken ribbon gently floating in the tranquil darkness. Tonight, we're embarking on a journey back in time, far, far back to a moment that teeters right on the very edge of what science, in all its ingenuity, can currently perceive. We're talking about the very genesis of the universe, or at least the earliest point we can definitively point to and confidently declare, yes, that's a beginning. It's a tale woven not just from matter, light, and the relentless march of time, but also from the very concept of limits, of the inherent boundaries of knowledge itself. What does it truly mean to know something? What does it signify for a single fleeting moment to even exist in the grand tapestry of space-time? But fear not, dear listener. We won't get too far ahead of ourselves, plunging into the deep end of cosmic philosophy. We'll proceed slowly, with deliberate gentleness, taking our time to thoughtfully consider each step of this immense journey. And just before we truly begin, if you find comfort and perhaps even a touch of wonder in these quiet explorations through the vast expanse of time and the boundless reaches of space, if they gently nudge you towards sleep or simply provide a soothing balm for your mind after a long, demanding day, please consider giving that like button a gentle tap. It's a small gesture, but it helps other sleepy souls like yourself, find their way to this peaceful corner of the internet. One restful listener at a time. Now, let's begin. But not with a thunderous bang, not just yet. Instead, we'll start with a question that sits patiently beneath almost every other question we can possibly ask, a question that subtly hides in the darkest corners of astronomy, the intricate equations of physics, and the all-encompassing field of cosmology. Where did absolutely everything come from? It's the kind of question that feels impossibly vast, too immense for our minds to fully grasp. Bigger than the brightest stars, more expansive than the largest galaxies, bigger even than the very concept of thought itself. And for a considerable length of time, science, in its cautious and methodical way, simply didn't attempt to answer it. After all, how do you even begin to measure the beginning of time when time itself is the very thing that's springing into existence? How can you possibly explain the birth of space when your only tools for offering an explanation fundamentally rely on space already being present? But that scientific silence wasn't destined to last forever. In the early years of the 20th century, a significant shift began to occur in the scientific landscape. Not because someone had suddenly discovered the definitive answer, but because entirely new and intriguing clues began to emerge. Observations from powerful telescopes, carefully collected data, seemingly random dots meticulously plotted on graphs, and strange, almost ethereal fingerprints subtly imprinted on the canvas of the night sky. And slowly, painstakingly, a discernible pattern began to coalesce. Quiet yet unmistakable suggestion that the universe itself is not a static, unchanging entity, it's dynamic, evolving, expanding. The very fabric of space between galaxies is growing, stretching outwards, not because galaxies are flying away from each other like scattered debris from some cosmic explosion, but because space itself is stretching and expanding everywhere all at once in every direction. This radical idea of a universe in constant flux was initially met with discomfort, even resistance. For centuries, humanity had operated under the assumption that the cosmos was eternal, immutable, and unchanging. Even Albert Einstein, when he was first confronted with the profound implications of his own groundbreaking equations, famously introduced a cosmological constant into his theory of general relativity. This constant was essentially a fudge factor designed to artificially cancel out the possibility of expansion, not because the underlying math demanded it, but simply because the very idea of a dynamic universe seemed too strange, too inherently unstable. He would later, with characteristic intellectual honesty, famously refer to that particular adjustment as the greatest mistake of my career. But as more and more observational data poured in from observatories around the world, the mounting evidence became increasingly difficult to ignore or dismiss. In the 1920s, the American astronomer Edwin Hubble made a truly transformative discovery that forever altered our understanding of the cosmos. When he meticulously studied the light emanating from incredibly distant galaxies, he noticed a rather peculiar and unexpected phenomenon. The light from these galaxies was stretched, shifted towards the red end of the spectrum, as if it were being pulled away, elongated. And what was even more intriguing was that the farther away a particular galaxy was, the more stretched, more redshifted its light appeared to be. It wasn't simply that some galaxies were receding into the depths of space. All of them were. And the farther away they were located, the faster they appeared to be moving away from us. This distinct pattern could only logically point to one inescapable conclusion: the universe itself was expanding, not in the sense of galaxies physically flying through empty space, but with space itself growing, stretching, slowly but surely carrying the galaxies apart from each other, like raisins embedded in a loaf of bread slowly rising in the oven. It was a profoundly radical idea, challenging centuries of established scientific thought, but the overwhelming weight of the accumulated data unequivocally supported it. And if the universe is demonstrably expanding today, then it logically follows that in the past it must have been smaller, denser, hotter, wound tighter and tighter into some earlier, more compressed state. The further back in time you attempt to rewind the cosmic clock, the more extreme conditions become. Eventually, this logical reasoning led scientists to a truly remarkable and almost unbelievable conclusion: if everything is relentlessly spreading apart now, and if that fundamental pattern continues consistently as you rewind the clock backwards, then at some point in the distant past, the entire universe must have been compacted into an incredibly hot, unimaginably dense state. A state where all of the matter, all of the energy, all of space itself, and perhaps even time itself, may have been compressed together, not necessarily into a single, infinitely small point exactly, but into a state so mind-bogglingly extreme that our current understanding of physics simply begins to break down and cease to be applicable. This concept became the very foundation for what we now commonly refer to as the Big Bang Theory. A somewhat misleading and perhaps unfortunate name, since it wasn't really a bang in the traditional sense of an explosion occurring within space. There was no pre-existing space for the explosion to expand into, because space itself was in the process of beginning. There was no sound, no light in the way we normally perceive it, just an unfolding, an emergence of everything everywhere all at once. A moment when the universe didn't expand into space, but rather created space as it expanded. It's important to pause here for a moment and carefully consider what we've just discussed, because this is precisely where science currently meets its frontier, its present-day horizon. The Big Bang Theory, as elegant and comprehensive as it is, doesn't actually describe the very beginning. It describes everything that happened after the universe began expanding. It provides us with a robust framework to understand how the cosmos evolved, step by step, from that incredibly hot primordial fireball to the cool, structured universe we observe around us today, filled with galaxies, stars, and planets. But the actual moment of beginning, the precise and exact nature of time, space, and even causality itself, before that initial expansion, remains shrouded in mystery, hidden behind a veil of scientific uncertainty. We simply don't yet know what, if anything, came before, and to be perfectly honest, we may never know. So, let's shift our focus and look more closely at what we can actually say with a reasonable degree of certainty about the Big Bang, not as some abstract philosophical idea, but as a series of concrete physical events that unfolded in a specific sequence. We don't begin with a singularity in the classic sense, at least not in the simplistic way it's often described in popular science. A true singularity, as mathematicians and physicists define it, implies a point of infinite density, infinite temperature, and infinite curvature of spacetime. While Einstein's theory of general relativity certainly points in that direction, the principles of quantum mechanics simply do not tolerate infinity so easily. What we're really dealing with is a frontier, a boundary point beyond which our current models and our present-day understanding of the laws of physics completely breaks down, not because there's necessarily nothing there, but because the mathematical tools we currently possess no longer work reliably. But what we do know with a reasonable level of confidence is this. The earliest moment we can meaningfully describe with our current scientific toolkit is called the Planck epoch. This is the very first infinitesimally tiny sliver of time after the universe began its initial expansion, just 100 million trillion trillionths of a second after the hypothetical beginning. That number is almost beyond human comprehension. To put it into perspective, if you were to stretch the entire 38 billion year history of the universe across the entire width of your living room, this Planck epoch would be smaller than a single microscopic grain of dust. It's a scale where gravity, quantum physics, and the very fabric of space-time itself are all tangled together in ways that we simply don't yet fully understand. During the Planck epoch, the universe was unimaginably small and incredibly hot, far beyond anything we can currently create in a laboratory. All four of the fundamental forces that we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are theorized to have been unified into a single, all-encompassing superforce, not just acting together in concert, but actually fundamentally indistinguishable from one another. A single unified force embedded within a seething quantum froth of rapidly fluctuating energy and highly curved spacetime. Unfortunately, we currently lack a complete and self-consistent theoretical framework that can adequately describe this exotic state of matter and energy. That's precisely why one of the greatest and most sought-after goals of modern physics is to develop a comprehensive theory of quantum gravity, something that can elegantly blend Einstein's theory of general relativity, which governs the behavior of gravity on large scales, with the seemingly contradictory principles of quantum mechanics, which governs the behavior of matter and energy on the smallest scales, into a unified description of nature at its most extreme. Until that scientific breakthrough occurs, the Planck time will remain a distant horizon, a boundary that we can approach but cannot yet fully cross. We can't directly see past it, but we can approach it, examine it, and reasonably describe what most likely happened next. As the universe relentlessly continued to expand, and just as importantly as it continued to cool from its initial incredibly hot state, the unified forces began to separate from one another in a process known as symmetry breaking. First, gravity, the force that governs the attraction between massive objects, split off from the other three forces. Then the strong nuclear force, which binds protons and neutrons together within the nuclei of atoms, separated. And as temperatures continued to fall, the electromagnetic force responsible for interactions between charged particles and the weak nuclear force, responsible for radioactive decay, finally parted ways as well. These weren't chaotic, violent events, but rather relatively smooth transitions, much like the different phases of matter emerging as a hot liquid gradually cools and solidifies into a crystal. With each step in this process, the universe became increasingly structured, more differentiated, and new possibilities emerged for the formation of complex structures. One of the most dramatic and significant changes came shortly after these initial force separations, a moment in cosmic history known as cosmic inflation. According to the prevailing theory of inflation, the universe didn't simply expand at a steady pace. Instead, in a tiny, almost unimaginably small fraction of a second, it ballooned outward with incredible speed. Space itself expanded faster than the speed of light. This doesn't violate Einstein's theory of relativity, since it wasn't a matter of objects moving through space, but rather space itself stretching and expanding. The sheer scale of this inflationary growth is staggering. Less time than it takes light to cross a single atom, the entire observable universe may have grown from a subatomic speck to something large enough to eventually contain billions upon billions of galaxies. Why did this happen? We're not entirely sure, but one of the leading and most compelling ideas is that a high-energy field, often referred to as the inflaton field, briefly dominated the energy density of the early universe. This hypothetical field triggered the period of exponential expansion and then subsequently decayed, dumping its immense energy into the cosmos and creating a uniform bath of particles and radiation. That event is sometimes referred to as the reheating of the universe, and it marks the start of what we usually think of as the Hot Big Bang, the moment when fundamental particles, atoms, and light began their long journey toward forming the complex structures we see today: nebulae, quasars, stars, and galaxies. After inflation ended, the universe was filled with an incredibly hot, dense plasma, a seething mixture of fundamental particles, high-energy radiation, and antimatter. Protons and neutrons began to form from the raw energy and then combine through nuclear fusion into simple atomic nuclei. This process, called primordial nucleosynthesis, occurred just a few minutes after the Big Bang, and it played a crucial role in determining the basic mix of matter that we observe in the cosmos today, mostly hydrogen, a significant amount of helium, and trace amounts of other light elements such as lithium and deuterium. It's truly astonishing how much was decided in those fleeting early minutes of the universe's existence. The delicate balance between matter and antimatter, the overall density of the universe, and even the initial seeds of structure that would one day grow into the vast cosmic web of galaxies were all largely baked in during this brief chaotic period, governed by physical laws that we're still striving to fully understand. But one thing is clear. By this point, the universe was no longer just a quantum fluctuation or some abstract mathematical concept. It was a real place filled with energy, motion, and immense potential. And yet it was still opaque. Light couldn't travel very far because it kept constantly bouncing off charged particles within the dense plasma. The universe glowed with intense heat, but not with visible light as we normally perceive it. It would take hundreds of thousands of years before the cosmos cooled sufficiently for electrons to settle into stable orbits around atomic nuclei, forming neutral atoms and finally allowing light to travel freely across vast distances. When that significant transition finally occurred, the very first photons of visible light began to stream unimpeded through space. That light is still with us today, stretched by billions of years of cosmic expansion. We call it the cosmic microwave background, and it represents the oldest light we can possibly see, a faint echo of the early universe. Let's pause here for a moment and focus our attention on the faintest light in the sky, a faint glow that isn't tied to any particular stars or galaxies, but something far older, something far more fundamental, something woven directly into the very fabric of space itself. Roughly 380,000 years after the Big Bang, the universe finally cooled enough for electrons and protons to combine together to form electrically neutral hydrogen atoms. This pivotal moment in cosmic history is called recombination, and it marked a dramatic shift in how the cosmos behaved. For the very first time, light could travel freely without being constantly scattered by free electrons. No longer trapped in a dense fog of charged particles, photons began to stream across space in every direction, like a radiant wave spreading outwards from the point of creation. That light is still traveling today, billions of years later. We call it the cosmic microwave background, or CMB for short. It fills the entire universe, not in isolated patches or streaks, but as a smooth, nearly uniform bath of radiation, like the faint afterglow of creation itself. It's not visible to the naked eye because the relentless expansion of the universe has stretched its wavelengths down into the microwave part of the electromagnetic spectrum. But it's still there, surrounding us, permeating everything like a faint whisper of ancient heat, a cosmic echo of the Big Bang. The discovery of the CMB was in many ways a fortunate accident. 1965, two radio engineers, Arno Penzias and Robert Wilson, were working with a highly sensitive microwave antenna at Bell Labs in Holmdel Township, New Jersey. They weren't actively searching for relics of the early universe. In fact, they were primarily focused on troubleshooting a persistent and unexplained source of noise in their instrument, a steady low-level hiss that wouldn't go away no matter where they pointed the antenna. They meticulously checked and recalibrated their equipment, ruled out potential sources of interference, and even went so far as to clean out nesting pigeons, suspecting that their droppings might be somehow to blame for the mysterious signal. But the persistent signal remained, stubbornly present no matter what they tried. What they'd stumbled upon unknowingly was the cosmic microwave background, the cooled remnant of the universe's earliest light. Nearly the same time, a group of physicists at Princeton University, just a short drive away from Bell Labs, had independently predicted that such a faint afterglow should exist, based on their theoretical calculations of the early universe. When the two teams connected and compared notes, it quickly became clear that this was a moment of extraordinary scientific significance. The Big Bang was no longer just a theoretical idea or a compelling mathematical model. It had left behind a tangible signature, a map, a direct imprint of the early universe that was still visible today, billions of years later. At first glance, the CMB appears astonishingly uniform. No matter where you look in the sky, its temperature is nearly the same, hovering just a few degrees above absolute zero, 2 to 73, 15 degrees Celsius, or 4 to 59, 67 degrees Fahrenheit. But as scientific instruments became increasingly sophisticated and precise, scientists noticed something remarkable. The seemingly smooth and uniform glow wasn't perfectly smooth after all. It possessed tiny, subtle ripples in temperature, minute fluctuations just millionths of a degree in size, barely detectable, but incredibly significant. These fluctuations are called anisotropies, and they represent tiny differences in the density of the early universe. In some places, matter was packed together just a little more tightly, in others, a little more loosely. Over billions of years, gravity would amplify those tiny differences, pulling matter together in some regions to form galaxies and stars, while leaving other regions relatively empty. Without those incredibly subtle ripples in the early universe, there would be no structure at all in the cosmos today. No galaxies, no stars, no planets, and ultimately no life. Just a featureless, homogeneous sea of light and gas. The CMB is in that sense a kind of baby picture of the universe, a snapshot of what it looked like when it was just 380,000 years old, long before the first stars ignited, long before Earth even existed. And by meticulously studying the shape, size, and scale of those subtle temperature ripples, cosmologists can effectively reverse engineer the ingredients of the cosmos. They can precisely measure how much of the universe is made up of ordinary matter, the stuff that makes up stars, planets, and people, how much is made up of dark matter, an invisible substance that exerts gravitational pull, and even how much is made up of something stranger still, dark energy, a mysterious force that appears to be accelerating the universe's expansion over time. One of the most important missions ever launched to map the CMB in exquisite detail was the Planck satellite, a sophisticated space observatory launched by the European Space Agency in 2009. Over several years of operation, it produced the most precise and detailed image we've ever had of the early universe. A glowing oval of subtle color shifts, each one marking a tiny difference in temperature and density across the sky. From the data gathered by the Planck satellite, we've learned that the universe is approximately 13.8 billion years old. We've refined our estimates of how fast it's currently expanding, and we've confirmed that only about 5% of the universe is made up of ordinary matter, the kind that makes up stars, planets, and human beings. The rest appears to be invisible, dark matter, which pulls on galaxies through gravity, and dark energy, which pushes the universe apart. And yet, even with all of that incredible insight, the CMB also marks the current limit of what we can directly observe in the universe, not because there's necessarily nothing beyond it, but because it represents the farthest light that has ever reached us across the vast expanse of space. Anything that happened earlier than recombination is still hidden behind a veil of glowing plasma, forever obscured from our direct view. To see any further back in time, we would need something other than light, something even older and more penetrating, and that inevitably leads us toward the next great mystery in cosmology, not what we can currently see, but what we can only infer based on indirect evidence and theoretical models. Let's return for a moment to the earliest moments after the Big Bang, not to the expansion itself, but to what it left behind in its wake: energy, heat, and eventually matter. One of the most profound and fundamental questions in cosmology is deceptively simple. Why is there something rather than nothing? The laws of physics, as we currently understand them, strongly suggest that matter and antimatter should have been created in precisely equal amounts during the Big Bang. For every proton, there should have been an antiproton. For every electron, there should have been a positron. When these opposite particles meet, they annihilate each other in a burst of pure energy, converting back into photons. In theory, the early universe should have been perfectly symmetrical, with equal amounts of matter and antimatter constantly being created and destroyed. And yet the universe we observe today is anything but symmetrical. When we look around today, we see a universe made almost entirely of matter. Antimatter is exceedingly rare and is mostly produced artificially in particle accelerators or during high-energy cosmic events. Somehow, in those first fleeting fractions of a second after the Big Bang, matter gained the upper hand. Not by much, perhaps only one extra particle of matter for every billion pairs of matter and antimatter, but enough that when all the mutual annihilations were complete, that tiny excess of matter was left behind. And from that seemingly insignificant remainder came everything, all the galaxies, all the stars, all the planets, and ultimately all of life as we know it. This fundamental imbalance, this triumph of matter over antimatter, is called baryon asymmetry, and to this day it remains one of the most intriguing and perplexing open questions in modern physics. What tipped the scales? Why did matter come out ever so slightly ahead? Physicists have proposed several potential mechanisms that might explain this mysterious asymmetry. One possibility is that the laws of physics themselves aren't perfectly symmetrical. There may be subtle processes that treat matter and antimatter just a little bit differently. These are called CP violations, short for charge parity violations. They've been observed in certain particle decays, but not yet to the extent needed to fully explain the overall imbalance we see in the universe. Another intriguing idea involves hypothetical particles that no longer exist in the present-day universe, heavy, exotic forms of matter that may have decayed in asymmetric ways during the earliest moments of the Big Bang. These decays could have favored the production of matter over antimatter in precisely the right amounts, setting the stage for everything that followed. But these particles are purely theoretical at this point. If they ever existed, they vanished almost instantly, leaving only their subtle influence behind. Whatever the underlying mechanism, the ultimate result was profound. That slight excess of matter, perhaps just one part in a billion, would go on to form every atom, every molecule, and every star in the observable universe. Without it, there would be no galaxies, no light, no chemistry, and no life. The entire visible universe is ultimately built on what might be described as a cosmic rounding error, a delicate imbalance subtly written into the very fabric of creation. And what's even more humbling and awe-inspiring is this: we don't fully know why it happened. Not completely. We can describe it in intricate mathematical detail. We can measure its consequences with ever-increasing precision, but the underlying cause remains tantalizingly out of reach, hidden behind a veil of scientific uncertainty. It's as if the universe has left us a tantalizing clue, but not the key to fully unlocking its secrets. And so scientists continue to search in particle accelerators, in neutrino experiments, and in the faint echoes of ancient radiation for any subtle sign of how the fundamental laws of physics might favor matter just enough to allow a universe like ours to exist. This scientific search isn't just an academic exercise. It touches upon some of the deepest philosophical questions we can possibly ask. Why is there something rather than nothing? Why do the laws of nature permit a world like ours to emerge from such a delicate and improbable beginning? These are not easy questions to answer, but science, moving slowly, gently, and step by step, can sometimes circle ever closer to the very heart of them. In the end, what we call the universe, the stars, the galaxies, the swirling arms of the Milky Way, and even the atoms in your very fingertips, all ultimately came from that leftover sliver of matter, that tiny imbalance that the early universe didn't quite erase. And from there, structure began to emerge. Gravity took hold, exerting its relentless pull on the surrounding matter. The densest regions of matter began to collapse inwards, drawing in even more material, heating up and compressing into ever smaller volumes. These dense regions would eventually become the first stars, not yet fully formed, but already destined for greatness. The universe, once remarkably smooth and uniform, was beginning to ripple, to clump, to become uneven in ways that would ultimately matter a great deal. But before those first stars could ignite their nuclear furnaces, before galaxies could begin to spiral into their majestic forms, and long before planets could take shape and orbit those distant stars, the universe had to pass through a long, quiet phase without light, without complex structures, and almost without a name. A time that cosmologists now refer to as the cosmic dark ages. And that is precisely where we'll go next on our journey through the history of the universe. The cosmic dark ages. The universe had light once, as we've discussed. That early glowing fog of photons was released when electrons and nuclei first combined to form neutral atoms, allowing light to travel freely. But that light gradually faded, stretched by the relentless expansion of the universe, thinned by the vast distances involved, and cooled by the passage of billions of years. And what followed was a kind of stillness, a darkness, a long cosmic night that enveloped the entire universe. This era is called the Cosmic Dark Ages, and it lasted for hundreds of millions of years, a significant chunk of the universe's total lifespan. During this time, the universe was still full of matter. Hydrogen and helium atoms drifted quietly through expanding space, slowly gathering into ever denser clumps under the relentless pull of gravity. But there were no stars to ignite, no quasars to blaze with brilliance, and no galaxies to illuminate the sky. The photons from the Big Bang still existed, but they were no longer visible to the naked eye. Their wavelengths stretched far beyond the visible spectrum, and no new photons had yet been born. If you could have somehow stood in the middle of space during this period, you would have seen absolutely nothing at all. No starlight, no planets, no nebulae, no movement beyond the slow, almost imperceptible gravitational collapse of vast clouds of hydrogen gas. The universe was vast, empty, and utterly dark. Yet, even in this apparent emptiness, the universe was quietly preparing for something astonishing, something transformative. Over time, millions upon millions of years, gravity continued its patient work. The denser regions of space pulled in more and more of the surrounding gas. Tiny fluctuations in density, seated all the way back in the earliest moments after the Big Bang, began to grow and amplify. These clouds of hydrogen gas collapsed slowly, deepening into increasingly dense knots of pressure and heat. And at a certain critical threshold, one that we know well from studying the behavior of stars today, nuclear fusion began. Hydrogen atoms began to fuse together under immense pressure, releasing tremendous amounts of energy in the process. The first stars flickered into being, igniting their nuclear furnaces and casting their light out into the darkness. They were likely much larger and more massive than most of the stars we see today, perhaps hundreds of times the mass of our own sun. These were population 3 stars, the very first generation of stars to form in the universe, born from pure hydrogen and helium, untouched by the heavier elements that would later be forged in the cores of supernova. They lived fast and died young, burning brightly and collapsing quickly into massive black holes or spectacular supernova explosions. Their light marked the end of the cosmic dark ages, not all at once, but gradually, as more and more of these primordial stars ignited. As these early stars ignited, they poured ultraviolet radiation into their surroundings, stripping electrons from nearby hydrogen atoms and turning cold, neutral gas back into an ionized plasma. This process is called reionization, and it slowly peeled back the veil of darkness that had enveloped the cosmos for hundreds of millions of years. Reionization didn't happen overnight. It was a gradual process that spread unevenly across space. The first stars tended to form in clusters, in tiny, primitive galaxies, and their radiation carved glowing bubbles around them, clearing pockets of transparency in the otherwise opaque darkness. Over hundreds of millions of years, these bubbles of ionized gas grew and merged, until finally the fog of neutral hydrogen was mostly gone and space became transparent and visible once again. This phase of the universe, from the ignition of the first stars to the completion of reionization, is incredibly difficult to observe directly. Light from those early stars is faint, distant, and stretched across billions of light years, but new and powerful telescopes, like the James Webb Space Telescope, JWST, are finally beginning to glimpse galaxies that formed just a few hundred million years after the Big Bang, offering our first direct look into that long-lost era. These observations are providing invaluable insights into the conditions that prevailed during the cosmic dark ages and the processes that led to the formation of the first stars and galaxies. These nascent galaxies were far from the majestic spirals and ellipticals we observe in the present-day universe. They were smaller, more compact, and significantly more chaotic, swirling cauldrons of gas and dust undergoing intense star formation. Yet within these tumultuous environments, gravity and nuclear fusion were hard at work, forging stars in prolific numbers. These early galaxies were in essence the very first stellar nurseries, the cradles where stars were born and nurtured. With the advent of these first stars came something entirely new to the universe: complex chemistry. Before this point, the cosmos was largely composed of hydrogen and helium, the simple elements forged in the Big Bang. The nuclear furnaces within stars began to transmute these lighter elements into heavier ones, creating the first traces of carbon, oxygen, iron, and all the other elements necessary for building more complex structures. These were the very building blocks of everything that would follow: planets, oceans, and eventually life itself. The first stars, unlike the smaller, longer-lived stars we see today, were behemoths, burning through their fuel at an astonishing rate. When they reached the end of their lives, they didn't simply fade away. Many of them met a spectacular end, exploding as brilliant supernovae that briefly outshone entire galaxies. These cataclysmic events scattered the newly forged elements across vast stretches of space, seeding the cosmos with the raw materials for future generations of stars and planets. Imagine these elements: carbon, oxygen, iron, and a whole host of others being flung out into the void, becoming interstellar dust motes, ready to be incorporated into new cosmic structures. This enriched material served as the foundation for the next generation of stars. Around some of these new stars, swirling disks of dust and gas known as protoplanetary disks began to coalesce. Within these disks, gravity worked tirelessly, drawing particles together. Collisions were frequent, and slowly, over millions of years, these particles began to clump together, gradually shaping themselves into planetesimals, the seeds of planets. Meanwhile, the galaxies themselves were undergoing a transformation. They began to aggregate into larger structures, drawn together by the relentless pull of gravity. Galaxies collided, merged, and interacted in complex gravitational dances. Some settled into graceful spiral forms, their arms tracing out patterns of star formation. Others coalesced into massive elliptical galaxies, densely packed with older stars. On the grandest scales, the cosmic web began to emerge. This vast filamentary network of dark matter and galaxies stretched across the universe, connecting clusters of galaxies in a web-like structure. The universe was no longer a smooth, uniform expanse of darkness. It had become alive with light, complexity, and motion, a vibrant tapestry woven from stars, galaxies, and the invisible threads of dark matter. By around 1 billion years after the Big Bang, the universe had transitioned into a new era. It was an era that, in its broad strokes, resembled the cosmos we observe today. The universe was still evolving, still expanding, but it was now illuminated by the light of countless stars and shaped by the pervasive influence of gravity. The long cosmic silence had ended, and the symphony of the universe had begun, a grand composition of light, matter, and energy unfolding across vast cosmic distances. By the time the universe reached a few billion years old, it began to exhibit a sense of familiarity, at least when viewed from a great distance. Galaxies had fully formed, glowing brightly with the light of billions of stars, and were interwoven by gravity into enormous structures. Some galaxies had spun themselves into elegant spiral shapes, while others had clustered together into dense knots. Vast voids, nearly devoid of matter, stretched between these structures like bubbles in a cosmic foam. The universe, once uniformly dense, had evolved into a richly textured landscape of cosmic structures. And yet, despite all this change and evolution, one fundamental aspect of the universe remained constant: its expansion. Ever since the Big Bang, space itself had been stretching, carrying galaxies along with it. As galaxies moved apart due to this expansion, the light they emitted was also stretched, shifted toward longer, redder wavelengths. This phenomenon, known as cosmic redshift, provides one of our most valuable tools for understanding the scale and rate of the universe's expansion. The farther away a galaxy is, the more its light is redshifted, indicating that it is receding from us at a faster rate. The idea that the universe is expanding was first observationally confirmed in the 1920s, largely due to the groundbreaking work of Edwin Hubble. By carefully measuring the redshifts of distant galaxies, Hubble discovered a clear and unmistakable pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. It was as if space itself was stretching in every direction, carrying galaxies along with it like leaves on a flowing river. For many decades, scientists assumed that this expansion must be gradually slowing down. After all, gravity is a force that pulls things together. With so much matter present in the universe, it seemed logical that gravity would eventually counteract the expansion, perhaps even bringing it to a halt. Some physicists even speculated about a big crunch, a scenario in which the cosmos might one day reverse its expansion and collapse back into itself. But then, in the late 1990s, a truly unexpected discovery shook the foundations of cosmology. Two independent teams of astronomers, working separately, were studying distant supernovae, incredibly luminous explosions that serve as standard candles, allowing astronomers to measure vast cosmic distances with unprecedented accuracy. What they found was both surprising and profound. The expansion of the universe was not slowing down. Instead, it was accelerating. Some mysterious force or intrinsic property of space itself, was causing the universe to expand at an ever-increasing rate. This mysterious force has been given the rather unassuming name of dark energy. Dark energy is not a substance that we can see, touch, or directly detect. It doesn't glow, it doesn't clump together like matter, and it doesn't interact with light in any readily observable way. Instead, it appears to be an inherent property of space itself, a kind of energy woven into the very fabric of the vacuum, gently pushing everything apart. Today, cosmologists estimate that dark energy makes up roughly 70% of the total energy density of the universe. It is the dominant force driving cosmic evolution, and yet it remains almost entirely unexplained. We don't know whether its strength will remain constant over time or whether it might change in the future. We don't know what causes it, whether it is a true cosmological constant, as Einstein once proposed, or something more dynamic, like a slowly evolving energy field. What we do know is that dark energy's effects are profound and far-reaching. Over vast timescales, galaxies that are not gravitationally bound together will drift farther and farther apart. Eventually, distant galaxies will recede beyond the horizon of visibility, not because they are moving through space, but because space itself is expanding so rapidly that their light will never reach us. In the far future, the universe may become a much colder and lonelier place. Stars will continue to shine for a time, but beyond a certain point, only the closest galaxies will remain visible. The cosmos, once a vibrant and bustling arena of activity, will gradually fade into a state of quiet isolation. And yet, even in that distant, silent future, the universe will continue to evolve. Stars will age and die, some collapsing into white dwarfs, neutron stars, or black holes. New stars will occasionally be born from the scattered ashes of earlier generations, but over immense timescales, trillions of years into the future, the rate of star formation will slow dramatically. The cosmic fuel supply will gradually dwindle, fewer and fewer stars will be born, and the galaxies will slowly grow dim. One by one, the lights will go out, and the universe will eventually enter what some cosmologists call the degenerate era. This is a time dominated not by stars, but by their remnants, white dwarfs drifting quietly through space, neutron stars spinning silently, and black holes slowly consuming whatever matter falls within their gravitational reach. Time itself will stretch on without end, seemingly without purpose. Eventually, even the black holes may vanish, slowly evaporating over unimaginable timescales through a process called Hawking radiation. And if dark energy continues to accelerate the expansion of the universe, as it appears to be doing now, the cosmos may eventually thin out and cool down until it approaches absolute stillness, a state of near-perfect equilibrium. No stars, no warmth, just a sparse scattering of particles drifting through an ever-expanding void. But that is just one possible scenario. The future is vast, unknowable, and filled with profound questions. The universe is not static. It has never been. From the very moment of the Big Bang, it has been in a constant state of growth and change. Particles formed, light escaped, galaxies spun into being, and stars lived and died. And even now, billions of years later, everything is still in motion, still unfolding according to the laws of physics. But what lies ahead? If dark energy remains constant, if the force accelerating the expansion of space continues at its current rate, then the universe will become increasingly colder and darker over time. This scenario is sometimes referred to as the Big Freeze. It is a future in which expansion never ceases and in which eventually all the stars burn out, the black holes evaporate, and all that remains is a thin, silent fog of particles. It's not a dramatic ending, no cataclysmic crash or fiery explosion, just a long, slow exhale into stillness. However, the Big Freeze isn't the only possibility. Some physicists have envisioned a different ending, one in which dark energy doesn't remain constant but grows stronger over time. In this scenario, the acceleration of the universe would increase exponentially, eventually tearing apart galaxies, then stars, then planets, and eventually even atoms themselves. This idea is called the Big Rip. It wouldn't happen suddenly, it would unfold over billions of years, but in the final moments, space itself could become unstable, stretching so rapidly that nothing could remain bound together. Even the tiniest building blocks of matter might be pulled apart, ripped asunder by the relentless force of accelerating expansion. It's a more dramatic vision, and it is still highly speculative, but it is one that follows logically from a dark energy that changes with time. Then again, perhaps the expansion won't go on forever. Some cosmological models suggest that dark energy might eventually reverse its course, that the universe, after reaching a certain point of expansion, might begin to slow down and eventually collapse inward. This would be a reversal of the Big Bang, a scenario known as the Big Crunch. Everything would be drawn back together, the density increasing, the temperature rising until perhaps another explosion begins the cycle anew. From this idea, some have proposed the concept of an oscillating universe, a cyclic cosmos that is forever expanding and contracting, like the breath of some cosmic entity. A cosmos with no true beginning or end, only transitions, deaths that lead to births, collapses that spark new expansions, a universe that breathes in epics. The idea of a cyclic universe is an ancient one whispered in myths and legends long before science gave it formal expression. A cosmos with no true beginning or end, only transitions. Modern physics doesn't rule it out entirely. Some theories, such as loop quantum cosmology, suggest that the Big Bang may not have been the absolute beginning of everything, but rather a rebound, the result of a previous universe collapsing under its own weight. Others imagine even more complex scenarios, such as multiverses where our universe is just one bubble among countless others, or quantum fluctuations spawning new regions of space beyond our cosmic horizon. We don't yet know if these ideas are testable, or even if they are ultimately correct. They remain, for now, at the very edge of scientific speculation, but they emerge from real mathematics, real physics, and they offer something deeply human. A sense that the story may not be over, that the cosmos may contain more chapters than we can yet imagine, and yet even if the future is unknowable, the present is not. We are here in this brief moment of light between the darkness before and the silence to come. The future of the universe stretches far beyond our lifetimes, beyond stars, beyond galaxies. We are the same, we are not, we've spoken. If you're wherever, it helps. And now, and so, music.